Welcome back once again to Join Academy. In our previous video, we were able to look at the action potential in the atria. There is every need for you to watch the video so that you can flow along. Use the link in the description of this video. In this video, we will be looking at the other special conducting tissues of the heart. Atrioventricular node being one of them. The atrioventricular node is located on the endocardial surface of the posterior and right border of interarterial septum, near the mouth of the coronary sinus. It developed from the left side of the body and therefore receives the vagal and sympathetic innervation from the left side. The rate of spontaneous depolarization of the AV node is about 40 times per minute. Three special muscle fibers help in the conduction of impulse from the SA node to the AV node. These special muscle fibers are Bachmann, also known as the anterior fiber, the Wenckebach fibers, which are also known as the middle fiber, and the Torel fibers, which are also known as the posterior fibers. Let us have a look at another special conducting tissues of the heart, known as the bundle of His. The bundle of His originates from the atrioventricular node and divides into the right and left branches at the top of the interventricular septum, which runs under the endocardium on the either side, and then terminates as the Purkinje fibers that penetrate the endocardium of the corresponding ventricular muscles. The left bundle branch is further split into an anterior and a posterior fasciculi. The inherent rhythm of the bundle of His is 20 times per minute. Having talked about these special conducting tissues of the heart, let us have a look at the action potential in these tissues. We will start with the SA node and the AV node. The action potentials in the SA node and the AV nodes are very different from the ones in other parts of the heart. Let's look at some of the differences. In the SA node and the AV node, the resting membrane potential is lower, that is about minus 60 mV, instead of minus 90 mV in the atria and the ventricles. Also, the resting membrane potential is unstable, and the reason for this instability of the resting membrane potential in the AV node and SA node is because the membrane spontaneously depolarizes and then triggers off action potential. This slow spontaneous depolarization is known as prepotential or pacemaker potential, and it is caused by entry of calcium ions into the channels due to the opening of the transient calcium ion channels. The faster generation of action potentials from the SA node depolarizes the atrium, including the AV node. Therefore, AV node on its own cannot generate action potentials. Other features that are peculiar only to the SA node and AV node is that the threshold potential is lower, which is about minus 40 mV compared with minus 60 mV in the atrial and ventricular muscle. Also, the action potential in the SA and AV node has no rapid upstroke and no plateau phase. In the SA node and AV node, the upstroke or depolarization is caused by the opening of the long-lasting calcium ion channel, which brings about the influx of calcium ion, and not by sodium ion influx. Then repolarization is due to potassium ion efflux. Let us also look at the action potential in the Purkinje fibers. The action potential in the Purkinje fibers is similar to that of the ventricles, but is longer in duration, and this ensures that the ventricles are fully repolarized and ready for another action potential before it arrives. Let us take a look at the speed which action potential travels in various conducting tissues of the heart. The special conducting tissues conduct impulse at different rates compared to the whole of the myocardium. In the whole of atrial and ventricular muscles, including the bundle of His, the rate is about 1 meter per second, and the rate is very slow in SA node and AV node, which is about 0.05 meter per second. But in Purkinje fibers, the speed is extremely fast, which is about 4 meter per second. The nodal delays and the rapid Purkinje transmissions are important for some reasons. One of the reasons is that since the AV node bundle of His complex is the only channel by which impulse travels from the atria to the ventricles, the delay in transmission of AV node allows time for the atria to contract and empty their contents before the ventricles contract. This delay is shortened by the sympathetic stimulations and prolonged by vagal stimulations. Another reason is that the rapid conduction of the Purkinje fibers enables impulse to reach all parts of the large ventricular mass immediately. Also, the slow conduction at the SA node prevents re-entry of impulse from the atria into the pacemaker. Another interesting unique feature of the myocardium is its syncytial behavior. Once action potentials are generated at the SA node, they are conducted from cells to cells throughout the atrium and then through the special conducting tissues to the ventricles, where again impulse spreads throughout the ventricle. The atria and the ventricles therefore behave as if they are continuous multinucleated cell masses that has no cell partitions. This behavior is not seen in skeletal muscle. In skeletal muscle, the impulse initiated in one muscle fiber spread only throughout that cell, and each cell has to be separately stimulated before it can eventually contract. The cell-to-cell conduction in the myocardium is as a result of presence of gap junctions between cells. The all or none law therefore applies to the entire syncytial membrane of the atria or the ventricles and not to a single membrane as in the skeletal muscle. The all or none law states that biological processes such as nerve impulses either happen completely or do not happen at all. This means that if stimulation is strong enough, the response will be complete, but if it is not strong enough, there will be no response. The next video will be on the different factors that affect the heart rate. I hope to have you watch the next video. Do not forget to subscribe and share. See you next time.